Adversarial, and I'm here to present Multiexpert Adversarial Regularization for robust and data efficient deep supervised learning. So realize that you have data distribution that evolves over time, and the modules also encounter new scenarios. So you want to find a way in case there is a mismatch between train and test data in the network, in the neural network, and they don't have a robust kind of generalized way across to the different scenarios that may come across in time. How can we handle this mismatch? So we have what we call data augmentation, that is whereby we can diluting the undesired signals, or trying to do transformation of existing examples to ensure that it can address robustness and regularization challenges. So by using Multiexpert Adversarial Regularization learning, we are going to be handling, we are going to train a module using multiple experts and feature extractor in an adversarial way, whereby you're training the model to how it can spot an intentionally misleading data. It is intentionally misleading data or behavior, but we want to see and want to achieve this by using, if we take a look at the MEAR model, we want to give input will be our weakly augmented and then strongly augmented augmented examples. That is, when I say weakly augmented, can be like you change a little bit, there's a very little difference, a small difference with the original image, or there is something that was changed, something later that was changed. We are going to look at those few features that were changed in the weakly augmented. Then strongly augmented, more extra distinctive features were changed, and it is not easily recognizable compared to the original image. So here we have the module that we are going to use consists of a feature extractor F that is having K with H1 and H2. These are experts whereby we are going to train them to minimize the supervised loss, that is LS, and it will be minimizing supervised loss on weakly augmented samples, and to minimize the diversity loss on strongly augmented samples. So when you take a look at the blue arrow moving from the blue arrow and the red arrows, showing you the weakly augmented samples and the weakly and the strongly augmented samples, it is helping us. It is showing you that H1 is going to be trained. H1 and H2 will be trained with minimizing the supervised loss on weakly augmented samples and to minimize the diversity loss on strongly augmented samples. But about F is the feature extractor, and for it we want it to, of course, also minimize the supervised loss on weakly augmented samples and to minimize the multi-expert consensus loss on strongly augmented samples. So what will we achieve at the end of the day? We want to propose, they were proposing this particular system whereby a single input, it will be a single input multi-prediction network enabling multiple predictions in a single forward pass. And then they also introduce multi-expert diversity from different scenarios that will be tested, and so that it can as well be as regularization term, they effectively reduce the redundancy among experts and to improve the accuracy of the assemble. And then, of course, after doing through experience, they want to validate this framework on various benchmarks, benchmark data sets, to demonstrate its superior generalization performance in low data region, and it has the ability to learn representations robust on variations across environments. So for the proposed method, It will mainly also improve the assembly generalization and robustness by using expert knowledge. It to teach the feature extractor and other experts in the adversarial manner, a manner whereby you put some resistance or some opposition to the scenario and to see how the model will respond, and this will help us in robustness. So it will also help us to be able to use weak argumentation and strong argumentation for input images to train the model. These both functions, they can perform label preserving transformation. So when it comes to weak argumentation, these are some of the points: the scale, the shift, color jitter. And then for the strong argumentation, it will be focusing mainly on shearing, rotation, auto contrast, sharpness. As you can see here, you see the first row at the top. The left is the original image, and then the rest of the top row is the weakly augmented images. As you can see them, you can clearly a little bit there it is in. So we have another option, which is the segmentation, semantic segmentation, which is different from the image classification. Now this one is about us having the random picks of the different as you see, the auto contrast, color, brightness. So we have a random pick, then we compare it together with the original image and we take it to data augmentation. Then from there it will be processed. So after being processed, we shall get after being combined with the original image, it will be fed into the semantic segmentation feature. Then all the obtained features will be sent to one expert head, that is the blue or orange solid line, for calculating the supervised loss. That one, the blue ones that you see. But then with here, we also want the augmented features will be sent to different expert heads for calculating the multiple expert advisory diverse loss and then consensus loss. So during the prediction time, only the orange line operator will be extracted, while the single segment feature will be sent to different expert head. And then you can see multiple expert heads, whereby they will be receiving the final predictions. These are the data sets that they are considering for classification and then for semantic segmentation. So when you see the training details, of course for weak augmentation, they focus mainly on color jittering, grayscale conversion, horizontal flip, channel-wise color, something that is a bit weak. And of course for the strong augmentation, they focus mainly on auto contrast, invert, as we saw it from the other table. So mean classification accuracy as percentages, you realize that with MEAR, it is high in terms of when you compare it with the standard mix-up or augmentation mix. These are all other modules that are existing, and you compare it with this particular proposed model, you realize that it is the MEAR is performing better than compared to the others. The same applies to this. So when you put it even on the graph, you realize that with the MEAR, it is performing accurately when it comes to comparison with the other methods that are used on clean test sets of data. And of course, even if we we try to compare we use corruption data or data that has been altered or played around with in terms of accuracy, you realize that still the MEAR is the black one that you see. Still you see in terms of accuracy it is high. And then it is even when you go to the feature visualization, realize that the first one is the original feature, the one in the middle is the one of learned features by standard method, and the last one is the one of MEAR, whereby it distinguishes the colors. You can clearly see that this is red, this is green, this is blue.